Solving trigonometric equations. So we are going to be using some algebraic techniques to solve trig equations. Let's get started. So here's our first example. All right, let's take a look at our first example. I have a cotangent on both sides of the equation here, and a lot of times students are tempted to divide both sides by a cotangent, but you never want to divide both sides by something that could be equal to 0. So instead what I'm going to do is set this equation equal to 0 and then take out the greatest common factor. So there I set it equal to 0, and I factored out the greatest common factor, and now I'm going to set each term equal to 0. So cotangent x equals 0, cotangent squared x minus 2 is equal to 0. I want to solve both of these for their trig function. This one is already solved for the cotangent. Over here I'm going to isolate the cosine squared. So I'm going to add the 2 first and then take a square root. Now here I run into problems because, as you know, the square root of 2 is larger than 1, and cosine can never be larger than 1. Nor can it be smaller than -1. So we actually don't end up with a solution from that particular piece. But over here, there are places where the cotangent is equal to 0. So you're going to want to look at your unit circle. So here I have the unit circle, and if we want the cotangent to be equal to 0, and remember cotangent is cosine divided by sine, so we want a place where the cosine is 0 and the sine is not 0. And that happens right here at pi over 2, and then again here at 3 pi over 2. And I don't just want those two answers. I want all the possible answers. And so, of course, we can go around the circle as many times as we want. So I'm going to write that my answer is, you could say pi over 2 plus 2 pi n, which would always have you hitting right up here. And then you can also write 3 pi over 2 plus 2 pi n. But because pi over 2 and 3 pi over 2 are always pi units away from each other in either direction, I'm actually going to write that x is equal to pi over 2 plus pi n. But again, you could write x equals pi over 2 plus 2 pi n, and then also x equals 3 pi over 2 plus 2 pi n, and that would also be correct if you wrote both of those. But if you want to be more efficient and precise, then you can write it this way. So what I said before about never dividing by a function, that's very important. And if you had done that, if you had divided this equation by cotangent from the beginning, then you would have just canceled out or gotten rid of that cotangent, and that's the one piece that actually gave you a solution. You would have ended up with no solution if you had done that here. On a very simple level, if you think back to like algebra 1, when you were solving something like x squared equals 2x, you never would have divided both sides by x. It's the same principle here. Instead, you would set that equal to 0, and then factor out the x, and then you could set each piece equal to 0, which was the exact technique that I did up here. So, it doesn't matter, because sometimes when you the thing that you were going to divide by, sometimes that leads to no solution from that particular piece, but that doesn't matter. You still don't ever want to do anything to divide by something that could be equal to 0 in an effort to cancel it. So here's another situation where students are tempted to divide both sides by sine of beta, but again, you don't want to do that. You want to just set it equal to 0 and then factor out that function, and then you would continue on from there. You might be thinking, but there have been times where we divided both sides by a function. And when you think about, like, when we were generating the Pythagorean identities, I divided both sides by cosine squared in order to turn that into a tangent squared. But I wasn't dividing by a cosine squared in order to get rid of a cosine. I was dividing by a cosine squared in an effort to change this into a different function. So they have different purposes there. So if you're trying to divide by something in order to get rid of it, that's what you have to be careful of. You can never divide by a function or a variable that could be equal to 0. You can divide by constants all the livelong day if you want. So in this section, some of the strategies that you're going to want to try are look for ways to factor or FOIL or solve, just like a quadratic equation. You're going to try to convert the entire equation to just one trig function if it's possible. If you're stuck, you can square both sides, but then you're going to have to check the solutions. But again, never divide by a trig function in an attempt to cancel it. Let's have a look at some more examples. So here, this is a quadratic one, but I have two different functions, which is no good because I only want one function. So I'm going to use the Pythagorean identity in order to substitute sine squared with cosine squared. Remember, sine squared theta plus cosine squared theta is equal to 1. So that means the sine squared theta is 1 minus cosine squared theta. So I'm going to substitute that. And then I'm going to distribute the 2, collect my like terms. Now, I don't like to have a negative quadratic term, so I'm going to multiply everything by -1. And then I'm going to factor that. And if you prefer to use that U substitution that we've done in class, then you can do that. But we're sophisticated now. We can do it without the U substitution. We know that it has to multiply. These have to add up to be, or excuse me, they have to multiply to be 1. And then we're trying to get a negative 3. And so this is a 2 cosine, and it's going to be a 1 cosine. So if I make them both negative, then I'm going to end up with a negative 3 cosine. And the negative times the negative makes that a positive 1. So that works. Set each of these equal to 0. And we're going to have, I'm going to skip some steps here. Cosine x equals a half, then cosine x equals 1. So now we go to the unit circle. This one's easier, where cosine x equals 1. So that happens right here at 0 or 2 pi, and then every multiple of that. So we can just say that x equals 0 plus 2 pi n, or just, 2 pi n. Where the cosine is equal to a half, we have the cosine equal to a half here at pi over 3, and then again down here at 5 pi over 3. And so these are not 90 degrees away from each other in either direction, or even 180 degrees away from each other. So I actually have to write it as 2 separate statements. So pi over 3 plus 2 pi n, and then 5 pi over 3 plus 2 pi n. And there you have it. All right, so let's have a look at number 3. We have 2 different functions here, but neither one of them is squared, so I can't make a Pythagorean substitution. So what I'm going to do here is actually square both sides. When you square both sides of an equation, you actually create new solutions that may become extraneous. So we're going to have to check our solutions at the end. So over here, when you square that, you're going to have cosine squared plus 2 cosine plus 1 equals sine squared. And now, because I have cosine squared and cosine and then sine squared, I'm going to do like I did in the previous example and substitute the sine squared with 1 minus cosine squared. So I have it all in terms of just one function. And then when I collect my like terms and set it equal to 0, it's actually kind of nice because my constant term canceled. So I just need to factor out the greatest common factor and set each one equal to 0. Go ahead and divide by that 2, and go ahead and subtract the 1. And then, like we did before, we're going to want to go to our circle. Now, one thing that's different here is they don't want all solutions. They want only the solutions within the interval from 0 to 2 pi. Notice that we have a square bracket around the 0 and a parenthesis around the 2 pi because those are the same place. So if you want to include only the 0, but you don't want to include the 2 pi, if that's one of your solutions. So when we look on our unit circle, where is your cosine equal to, say, 0? Well, that happens at pi over 2 and at 3 pi over 2. And then the cosine is equal to negative 1 over here at pi. So from this piece, we end up getting pi over 2 and 3 pi over 2. And then over here, we end up getting pi. Now you have to be careful. You have to check your solutions. So you want to check them by going back into your original equation. If I check the pi over 2, we'd be looking at cosine of pi over 2 plus 1. Is that equal to sine of pi over 2? Well, cosine of pi over 2 is 0 plus 1. Sine of pi over 2 is 1. So that one works. And then if we check the next one, cosine of 3 pi over 2 plus 1, is that equal to the sine of 3 pi over 2? Well, cosine of 3 pi over 2 is 0 plus 1. Sine of 3 pi over 2 is negative 1. These are not equal, so 3 pi over 2 is actually not a solution, so I'm just going to cross it out. And then finally, we'll check the cosine of pi plus 1. Is that equal to sine of pi? Cosine of pi is negative 1 plus 1. Sine of pi, that's equal to 0, so that one works. So we actually only have 2 solutions for that equation. All right, now let's do some examples where we have multiple angles. In these situations, we're going to be looking at something like sine of k times u or cosine of k times u. So after we isolate the trig function and after we refer to the unit circle, we're going to have to go through and divide our result by k. So here's our first example. I want to isolate the tangent first, so I'm going to subtract the 3 and divide both sides by 3. And now we're going to go to the unit circle to figure out where is the tangent equal to negative 1. So tangent, of course, is not one of the coordinates that are on here, but remember tangent is negative in quadrants 2 and quadrants 4, and the tangent would be 1, or negative 1, technically, when the sine and the cosine are the opposite value. So we're looking here at 3 pi over 4 and a 7 pi over 4. Now, conveniently, 3 pi over 4 and 7 pi over 4 are pi units away from each other. So we can say that x over 2 is equal to 3 pi over 4 plus pi n. But we're trying to isolate the x, not x over 2. So let's multiply everything by 2, and we'll have x equals 3 pi over 2 plus 2 pi n. We didn't do any squaring of both sides, so I don't need to check my solution. For the next one here, I have for the next one here, I have a difference of perfect squares. So I'm going to factor the difference of perfect squares. For this next one here, I have a difference of perfect squares. So I'm going to factor the difference of perfect squares. So it's cosecant squared of 2x minus 2, cosecant squared of 2x plus 2 equals 0. Set each of these equal to 0. Go ahead and set that equal to 2 there. And then, of course, here when I take a square root of both sides, which would be my next step, I'd end up trying to take a square root of a negative value, which is not real. So we're going to rule that out. We don't get a solution from that piece. But over here, we're looking at cosecant of 2x is equal to plus or minus the square root of 2. Anytime you take a square root, you remember to do the plus or minus. A lot of students forget that. Now this is a little bit weird because when we look at our unit circle, we don't have any square roots of 2. We also don't have any cosecant. So let's think about, instead of the cosecant, let's think about the reciprocal function. Instead of, if the cosecant is equal to plus or minus the square root of 2, then the sine of 2x is going to be the reciprocal of that, which would be plus or minus the square root of 2 divided by 2. So now we just have to look on the unit circle, where is the sine positive root 2 over 2 or negative root 2 over 2? Well, that's happening in lots of places, in every quadrant, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Well, these angles, pi over 4, all these 4 that I just mentioned, they are all pi over 2 or 90 degrees away from each other. So the most efficient way to write that would be to say pi over 4 plus pi over 2n. And remember, that's not equal to x, it's equal to 2x. And then we're going to multiply everything through by a half to get rid of that 2. So I'll have actually x equals pi over 8 plus pi over 4n. Again, I didn't square both sides, so I do not need to check my solution. For our next example, we're going to go to our calculators and we're going to approximate a solution. So here's our equation. 5 sine of theta tangent theta minus 10 tangent theta plus 3 sine theta minus 6 equals 0. Looks like kind of a nasty little problem. Well, we have 4 terms, right? We've got the 5 sine tan, the negative 10 tangent, the 3 sine, minus 6. Whenever you have 4 terms, you may recall from algebra that the type of factoring that you're going to want to try here is to factor by grouping. So if I look at the first 2 terms here and the second 2 terms here, and I take out their greatest common factor, well, from these first 2 terms, that would be 5 tangent of theta, and I would be left with sine of theta minus 2. And then over here, the greatest common factor would be 3, and I would be left with sine of theta minus 2. If it's appropriate to factor by grouping, and if you did it correctly, then what you have left in these parentheses will be the same. And actually, that becomes one of your factors because you've taken that out. So let's write that again, sine theta minus 2. And then the stuff that's in the front here is what you would have remaining. So 5 tangent of theta plus 3, and of course that's equal to 0. So we'll set each of these equal to 0. Sine theta equals 2. Let me go ahead and call that tangent of theta equals negative 3/5. Now over here, we're going to rule that out. We cannot solve that because tangent can never be bigger than 1 or smaller than negative 1. But there is a solution here to tangent equals negative 3/5. So I'm going to do this one in degrees. It didn't specify that I had to do it in degrees or radians, but degrees are a little easier to think of. So let's do that in degrees. So if I go to my calculator, let's take my mode. I need to change over to degree mode. And I'm going to do second tangent of negative 3 divided by 5. And that's happening at like about negative 31 degrees, we'll say. Okay, so theta is about equal to negative 31 degrees. Now, it didn't say that we only wanted an answer in one particular quadrant or in one revolution of the circle. So we need to think about all of the places where the tangent could be equal to negative 3/5. So remember, tangent is negative in quadrants 4 and in quadrant 2. And then we now know that this angle right here is negative 31 degrees. The other place where it would be negative would be here in quadrant 2, and then that reference angle there would be the 31 degrees. And so those angles are actually 180 degrees away from each other. So we can say then that our answer, theta, is actually negative 31 degrees plus 180n. where n would be any integer. I think I've forgotten to mention that, where n is any integer. So any number that you plug in for n, any integer that you plug in for n, you're going to end up in either quadrant 2 or quadrant 4, and the tangent of that angle would be -3/5. Next, let's talk about using inverse trig functions, which we've kind of already been doing. All right, so this is another, we have a quadratic, but we have two different functions, but I can use my Pythagorean identities in order to make a substitution. Remember that 1 plus tangent squared theta is equal to secant squared theta. So I'm going to make that substitution. 1 plus tangent squared equal x minus 2 tangent of x. Let's go ahead and subtract the 4 and set equal to 0. And collect our like terms. Tangent squared x minus 2 tangent x minus 3 equals 0. So this factors. It's not that's not too difficult. So tangent of x minus 3 and tangent of x plus 1 equals 0. So here we're looking at tangent of x is equal to 3, or tangent of x is equal to -1. Well, -1, we did that one earlier. We know that tangent is equal to -1 at 3 pi over 4 plus pi n. Now, tangent of x equals to 3, you might be tempted to rule that one out like we did with the sine and the cosine, but remember your tangent can be bigger than 1. So if you wanted the exact answer, you can actually just say that x is the arctan of 3. So if I were to circle these would be the exact answer. And of course, if I wanted an approximate answer, well, this one, 3 pi over 4, we're just going to leave like that. But over here, to get my, oops, I should have said plus pi n, because the tangent is -1. Let me go back to the circle for a second. Remember the tangent was -1 here at 3 pi over 4 and 7 pi over 4. And so they hit every 180 degrees away from each other. And so that's true for all of your tangents, because your tangents are positive in quadrants 1 and quadrants 3. So even if you're like right here at like 10 degrees, the other place where that would have the same tangent would be over here at 190 degrees. So they're always going to be 180 degrees or pi units away from each other. So that's why we should say on here plus pi n. Let me fix that. Okay, so for the approximate answer, let's just go to the calculator and get, we're going to do this one in radians since I have the 3 pi over 4. Let me change my mode back to radians. An inverse tangent of 3, so about 1.249, let's say. So we can say 1.249 plus pi n, and then of course the 3 pi over 4 plus pi n. So if we gave that, this would be the approximate answer. So the whole point of this particular example is just that sometimes if they want the exact answer, you can't really get rid of the trig function. You just have to write it in terms of the inverse trig function and say the arctangent of 3 plus pi n. Okay, so for our last example here, we want to find the inverse of this arc cosine function and state its domain and its range. So let's just go ahead and switch our x and y and solve for y to find the inverse. I'm going to divide by 4 or multiply by 1/4. And then I'm going to take a cosine of both sides. And then I can multiply both sides by 3/2. So this is our inverse function. So we're done with part of the problem here. So if you want to find the domain and range of this inverse function, you might be tempted just to graph this, or just a regular cosine function, and then identify its domain and range. But that would be wrong, because this is not the fully defined cosine function as you know it, because it was based off finding the inverse of an arc cosine function. So it helps to remember what the graph of the mother cosine function, arc cosine function looks like, which is this. So this is just the graph of the inverse cosine. I'm in radian mode. This is what I put for my window. All right, and then here's the graph of it. This is the mother function of the arc cosine, and we've done some transformations to it. We've done a vertical stretch, and we've done a horizontal stretch. So it's been stretched by 4, and it's been stretched horizontally just a little bit, 2/3. So if you think about stretching this graph vertically, that's of course going to change the range. So by multiplying everything by 4, it's just going to sort of pull it up from, instead of going from 0 to pi vertically, it's going to go from 0 to 4 pi. So for this one, the range of this one, the range of f, would be from 0 to 4 pi, and then the domain of f, well, the domain of the mother function is from -1 to 1, And we're going to be sort of stretching that out by the, you multiply by the reciprocal of that. So the domain of that, instead of multiplying it by 2/3, remember you do the reciprocal when you're on the inside there. So that's going to go from, instead of from -1 to 1 horizontally, it's going to go from -3/2 to +3/2. So -3/2 to +3/2. So those are for f, but we wanted to give the domain and the range for f inverse. So that means we just switch them. So the domain of f inverse is going to be the 0 to 4 pi. And then the range of f inverse is going to be from -3/2 to +3/2. And you could graph that in your calculator to check it.